Welcome. My name is Derek Carter, and in this video, we're going to continue looking at the XV6 operating system. So this is over chapter 2. So chapter 2 is titled Operating System Organization. I kind of think of this chapter as we're going to start digging deeper into the abstractions that an operating system provides. And this is some of the details about the process abstraction. So a little bit about the hardware mechanism, so supervisor mode versus user mode that the hardware provides. And that is the basis for how we can implement system calls that are basically the heart of the kernel operating system. So in this first video, it's just a bit of an introduction. As usual, I'm going to break these up into a couple of different pieces. So if you're ready, let's go ahead and get started. So the first part of our textbook is about isolation abstractions, about abstractions in general. This applies to any kind of operating system that's meant to be used for general purpose computing. So basically, most any general purpose operating system must fulfill 3 requirements. So it has to support multiplexing, and you can also think of this as supporting the management of resources. Okay, so an operating system has resources, and it's going to have to time share. It's going to have to share those between different entities that we usually think of as processes. So we have multiple processes running concurrently on the operating system, and the operating system has to keep track of resources such as the CPU, memory, open file devices, and other things, and successfully share those among processes. And it also has to provide for isolation. So you can also think of this as providing for protection or security, so that the independent processes running on the system can't interfere with one another. So an operating system must arrange for isolation between processes for various very good reasons, both because there are unintentional, unavoidable bugs. So, it's easy to write programs that accidentally write past the end of the array, and that could end up writing past memory that some other process owns if we don't have these kinds of isolation mechanisms implemented in the computer. Okay? But, there can be intentional trying to break isolation to get access to other processes or other bits of memory or data that you shouldn't have access to. So this is the beginning of computer security. So we don't, in general, an operating system can't assume good intentions among the processes that it's managing. Okay, so in the previous chapter, I might not have had this in the video, but usually the operating system, the people that are implementing the operating system kernel assume that the kernel code is well tested, has good intentions and things like that. So things in the kernel code are not assumed not to be things that intentionally have bad intentions or exploits. But that doesn't hold for user processes. So we have to set up the operating system, and we need support mechanisms from the hardware the operating system runs on in order to successfully provide isolation mechanisms. Okay, so I'm jumping ahead here a little bit, but the 2 main ones are we need hardware support for some sort of a supervisor or kernel mode versus a regular user mode, so some sort of mode. We need some sort of hardware mechanisms that provide memory management, so memory protections and things like virtual memory. And like a third kind of requirement, it should be possible. So we want the default to be that processes are isolated and can't affect one another unless they want to. Okay, so it should be possible for processes to intentionally interact. So really kind of that pipe, that shared buffer, is one way that can happen. Okay, so when we looked at the simple example of a pipe, we actually forked and exec a new process they shared the file descriptors on the two ends of the pipe. So they were actually using a pipeline to pass data. Output of one process became the input of another process using a pipeline. There's many other kinds of sharing mechanisms. We probably won't talk about some of these others, but there's shared memory and other things. Okay, the basic reason about that is that some problems are more easily solved and have better performance by implementing them as parallel applications rather than as just a completely sequential application. So even if you don't have a true multi-CPU system, still sometimes parallelism can get you boost in performance. So sometimes you've got some things that are going to be waiting for disk I/O, but while it's waiting for disk I/O, I can be doing calculations and switch back and forth between those two things even within the same sort of task or application. So an aside on the RISC-V architecture that we're using for the XV6 teaching operating system in this course. So XV6, we've mentioned RISC-V before, okay? So, RISC-V is a new, completely open source computer architecture specification, right? So completely open source. Anybody's free to get the specification and build chips based on the RISC-V specs. And it's lately, I think RISC-V was sometime in the 2010s or something like that. But it's lately kind of become much more ready for prime time. So you're beginning to see actual implementations of RISC-V microprocessors trying to do things in like the server space or other things like that. So I'm not really a computer architecture guy, so I don't know a whole lot about this. And another thing is that like I said in this course, I assume that you can pick up C even if you've never programmed in it, including if you've never done any things with pointers and memory management stuff. You might need to spend a little bit of time tutoring yourself to pick up some of those things. The same I could say about assembly code, the RISC-V assembly code. So we won't have a lot of it, but and I definitely don't assume that you've ever programmed some assembly, but I will assume that you can pick up kind of the basics. And RISC-V assembly is quite simple, even compared to ARM. So RISC-V, as the name would imply, is what's known as a reduced instruction set computer architecture. Which the ARM architecture, if you're familiar with that, is also considered a RISC architecture, and you can contrast those to the Intel x86, kind of one of the first big computer architectures, which is usually considered an example of a complex instruction set architecture. So our XV6 is written in this LP64C, so long pointer 64. So it really is a 64-bit architecture. Another thing is that we're running it using emulation, but our emulator can emulate a multi-core CPU. So we can also use that. The XV6 code is truly multi-core capable. So it can be using two or more true parallel cores when it's executing, or emulating thing in this case. There's some links here. I may in this course give you some things to read or more specific stuff. This link to the RISC-V reader is really a link to the Internet Archive, so it's really just a sample. So I believe that this book must still be under copyright, so I'm not certain if it's easy to get that without buying it. I mean, you can probably get it somewhere, but so even though this is relatively old, I'm not certain if there's, but again, it's an open source spec, so you can actually just pull up the full unprivileged and privileged spec for RISC-V. So this will have all of the opcode, all the RISC-V instructions, and what they work, and the parameters, operators they take, and all that kind of stuff. So, and finally, before I move on, I think I pointed this out before in a previous video, but whenever you run the quick emulator, one of the flags it uses is the dash machine virtual. So, I mean, that's some simulated hardware. So this basically sets up some simulated RAM and a ROM that contains the boot code that sets things up and actually, sets the things into the first machine mode that I'll talk about here in a second, and starts the fetch execute cycle at a particular known location in RAM. As well, there's like a basic serial connection that could be used for like a keyboard and terminal output, things like that. So this is a little bit of a review of some of the stuff we did in the previous chapter. So just reminding you that one way to think about what the kernel API of an operating system is doing is it's providing abstractions that can be used by regular user processes, to use and successfully share the computing hardware. So, we looked at, I kind of grouped them into 4 groups, kind of the same 4 that we talk about here, although mixed up a little bit. The open, read, write, and close, you can think of as part of the file descriptor abstraction. So I think of these more as the file descriptor abstraction. So these are a way for abstracting devices or files as just seeing them as streams of bytes that you can send, like as the output from one application to become the input of another, or as a stream of bytes to go to and from a permanent storage like a file system. The file system I would consider as kind of another one, a little bit separate from the file descriptor. So the file system abstraction provides high-level abstractions that are useful for doing non-volatile storage out to a hard drive. So things like path names, things like that. So even if isolation is not considered, the convenience of the open read write pipe and also the file system abstraction, so being able to make directories and a hierarchical file system and have path names in order to connect a file descriptor to read and write to permanent storage are all very desirable things for the user program. So I'll jump over. So, the fork exec, you can argue, these basically are what we'll talk about in more detail in the series of videos, are getting at the process abstraction and also the abstraction for memory access. So basically exec, when a new process is created, it actually creates a new virtual memory address space for the process and sets up the page table for it. Okay, so this relies on hardware mechanisms, those page tables. So like a memory management unit has to be provided by the hardware level, which we'll learn about. This is more of the next chapter 3 is on page tables and the virtual memory kind of abstraction. But we'll see some of this in this chapter as well about how the operating system builds images. Decides, builds basically the virtual memory address space, mapping processes, virtual address space into physical memory. But yeah, if there's one thing that this second chapter is about, it's mostly about the process abstraction. So we're going to see how the system initially boots up in the next video in this for this chapter here. And how it switches from the machine kernel mode to user mode. Talk a little bit about the process table and things like that. But basically, the process abstraction is how an operating system in general and basically all Unix-like operating systems manage and transparently switch between switch the CPUs among processes. Okay, so this is how it implements that time sharing. So the processes provide for isolation between processes through having different processes and having them have different virtual address spaces, and they allow the operating system to share, to multiplex hardware, CPUs, memory, file system, and other things like that. So I briefly reference the idea that the operating system, in order to successfully provide isolation or security, needs to have certain mechanisms provided by the hardware, the computer architecture hardware that the operating system is running on. Okay, so the one that's most relevant to process abstractions and the things we'll talk about for the process table in actually the next video is the dividing of instructions, or the implementation of some sort of at least two separate modes of execution of the CPU. Okay, so there needs to be one more privileged mode. So this goes by supervisor mode. A lot of people, you'll just hear this called kernel mode. I might switch back and forth between these when I talk about these. You might even hear it called just privilege mode. Okay, so you have to have a more privileged mode, at least at a minimum, in order to implement a modern operating system, and a less privileged mode, a user mode. And certain things have to be restricted, like the ability to set up page tables or the ability to execute particular instructions. It cannot be allowed to happen in user mode. It can only happen when we're running in supervisor mode. Okay, so this is one of the hardware mechanisms that a computer architecture needs to provide to implement a modern Unix-like operating system. This gives a hard boundary between applications and the OS. So for the RISC-V architecture, it actually has three modes, three privilege modes. I think ARM has four, if I remember right. Again, I'm not really computer architecture. I don't know how many like the Intel x86 has off the top of my head. So kind of the three that the RISC-V provides is a machine mode, a supervisor mode, and a user mode. So normally in our operating system, the x86 operating system we're going to look at is always either running in supervisor mode or user mode. So the machine mode is the actual initial mode that when you repower up or recycle the CPU in, it'll initially be in the machine mode. So this is mostly only used during boot, when the boot ROM comes up and starts the very first, sets up the program counter and starts the very first fetch execute cycle for the system. So one of the very first things we'll do, again in the next video when we look at the boot sequence for XV6, is we have to set up stuff to get us into supervisor mode initially, so that we can then create some structures and create the first user process and get prepared then to switch into user mode and start writing the first user process, the init process. So that's it for this video. So it's a bit of a short video, and it was only a discussion. The next video might be a bit longer, and we're going to actually get back into looking at the XV6 code, quite a bit of it actually. But what we talked about in this video is that there's three requirements that an operating system must fulfill: multiplexing or time sharing, and managing resources between multiple entities, the processes that run on the system; isolation or security, has to isolate processes so they can't affect each other; and interaction. So when they do want to interact, that should be possible. So the OS goal is to provide abstractions. You can think of this as the kernel APIs providing an application programming interface that provides a high-level way for applications, so they don't have to know all the messy details to do what they want to do. It makes it easy to write user applications on top of a general-purpose operating system. So the main abstractions that we talked about is file storage and devices are all accessed through basic file descriptor abstractions, which abstracts the movement of data as a byte stream to or from some source. That could be a file on a hard drive, it could be to like a device, keyboard, mouse device, whatever. The process abstraction, which this chapter is mostly about. We'll get into we'll look at the process table and some other things about processes, how it's implemented in the XV6 system. So processes are the basic abstraction that provide multiplexing and the illusion of complete control of the CPU. Right? And the fork exec set of system calls are mainly the ones that set up the process abstraction and also build the exec, since it's actually creating a new process, is the one that's setting up the new virtual memory address space for the new process. So you can kind of think of this one as the primary one, and this will be what we'll talk about in the next chapter, to implement the memory abstraction, the illusion of an address space that no other process has access to. Finally, we mentioned a couple times, but in order to get this kind of isolation, the operating system can't do it on itself just completely in software. So a modern operating system that's meant for implementing a general purpose computing absolutely requires that there's particular hardware support mechanisms in order to successfully implement the isolation of the security that we're talking about here. And I forgot to mention, I should have mentioned it. So the primary instruction in RISC-V is the eCall instruction. So this actually causes a change from user mode to kernel mode. So that's the initial step whenever we need to call a one of the kernel API methods. It'll start with an eCall instruction that calls the appropriate kernel method, shifting us into supervisor mode. And there'll be some more about that as well in this chapter. Okay, so that's it for this discussion. As usual, let me know if you have questions or feedback. I will have links to the things I mentioned in the video description and in our course additional resources. And I hope to see you in our next video then.